Welcome to Multiple Linear Regression Assumptions. In this presentation, we're going to talk about each of the 6 multiple linear regression assumptions and talk about what it means for them to hold. And here we have a list of the 5 assumptions that we need for our ordinary least squares estimates to be unbiased. And then we have the 6th assumption that we also need for it to be blue, or the best linear unbiased estimator. We're going to go over each of these in turn through this presentation. Assumption M1 or MLR1, whatever we want to call it, linear in the parameters. This assumption states that for OLS, ordinary least squares, to be unbiased, the population model must be correctly specified as linear in the parameters. This is the specification. We have our dependent variable y. This is our intercept, population intercept, and then these are each of our population slope parameters for each of our independent variables. We can see that our independent variables go from 1 all the way to k, and then the I is the observation number. So we have 1 to n observations. And then this is our error term, epsilon, that only lives in the population. It does not live in the sample. When is this assumption violated? Well, under 2 circumstances. The first one is if we specify a model that is nonlinear in the parameters. So we can see that ln, the natural log of beta 1, is not linear in beta 1, and so this would not be the same as or hold for our assumptions, and therefore this is a violation. This is an atypical violation. The second violation, number 2, is if the true population model is not specified correctly. And therefore, if the true population model is as this, so yi is beta naught plus beta 1, say natural log x1, and then the rest are linear. In this case, this is still linear in the parameters because it's still linear in the betas, but it was incorrectly specified. And therefore, if we estimated this model here, when this was the true model, this assumption would be violated. It's nearly impossible to see what the true model is. Our best case scenario is, first of all, doing scatter plots for each of our dependent variable versus our independent variables, or secondly, looking at what other people have done. But we'll never truly know whether or not our model is correctly specified. We just need to use our best guess. But this assumption is violated is if we estimate an incorrectly specified model. Assumption M2, the data are collected through simple random sampling. So this assumption states that for ordinary least squares OLS to be unbiased, the data must be obtained through simple random sampling. And this assumption ensures that the observations are statistically independent of each other across the units of observations. When is this assumption violated? Well, under 2 circumstances. First of all, a few. Obviously, if they're not collected using simple random sampling, that's when it's violated. Here are 2 examples. First of all, time series data are not collected through random samples because time series, we have the same variable over time, and therefore it's not a random sample. So in this case, if you're doing time series data, assumption M2 will be violated. And then secondly, the other kind of obvious way that this assumption is violated is if there's selection bias, or if you only sample a select group of people and don't have a random sample. For example, if individuals opt to be in a job training program, go to college, or the response rate of a survey is low, then you have selection bias and this assumption is violated. Assumption M3, this is the only one that's different relative to simple linear regression because it has 2 pieces to it. But this assumption states that the data are not perfectly multicollinear. So this assumption states that for OLS to be unbiased, each of the independent variables cannot all be the same value. So basically we need variation in each of our independent variables, or each of our x's. So this is j equals 1 to k. This is how many independent variables we have. So we have to have a positive variance, essentially, is what this says right here. And then this is the same thing that we assume for simple linear regression, that we had to have variation in our x. That's the same. The one additional component that this assumption has that simple linear regression doesn't have is that we need the independent variables to be not be a linear combination of another independent variable. So in other words, no perfect multicollinearity. And this assumption ensures that the slope estimator is defined, or our x prime x matrix is invertible for those of you like me who like matrix algebra. We typically don't violate this assumption in the sense that it's very, very rare to have all your x's the exact same value. And then secondly, it's not that common to have your x's be linear combination of other x's. How that could happen is if, again, you have square feet in feet and square feet in yards. Those would be linear combinations of each other. Nobody's doing that. The typical only way this assumption is going to be violated is if you fall into what we call the dummy variable trap, which admittedly we have not gotten to because that's chapter 7 material, but we'll talk about what that would mean within chapter 7. And basically that means that with dummy variables, we have to omit one of them, and if we don't, then this assumption will be violated. Again, we'll make this a lot clearer when we get to chapter 7, but in general, this assumption is not violated. Assumption M4, the error term has zero mean, so this is the expected value of epsilon, our error term, is equal to 0. And this will hold as long as the intercept is included in the model, because as we think about it, the intercept changes. It will recalibrate such that this assumption will hold. That's why we need an intercept in our model. So even if we don't care about the intercept, which many times we don't, we still should include it in our model unless we have a very, very good reason not to. Our last assumption for our OLS estimates to be unbiased, the error term is not correlated with each independent variable or any function of each independent variable. This is what I think of as the zero conditional mean assumption. This is the conditional aspect of it. So the expected value of our error term given, this is the conditional aspect of it, each of our x's is equal to 0. So this means that our independent variables are unrelated to our error term, and then also each function of our independent variables are not related to our error term. And so when is this assumption violated? Well, it is violated much of the time in economics because we have observational data. And so how to think about it is it's a thought experiment. You think about, okay, what things influence y that are not in my model? Those all live in my error term. And are any of those factors related to my x's? And so I guess what I say is think of all the factors that affect the dependent variable that are not specified in the model. For salary versus education, the thing that we always talk about is ability, which is very hard to account for. And then if ability is related to, say, education, then this assumption is violated. In this case, first of all, we never observe the error term because it lives in the population. So this, again, is something that is a thought experiment. We never know for sure whether or not it's violated, but I would say that probably 98 to 99% of the time in economics, when we do econometrics, this assumption is violated because there's typically something in the error term that is related to one or more of our independent variables. It doesn't have to be related to all of them, it just has to be related to only one of them for this assumption to be violated. So in general, the assumptions that we've talked about that are violated are M1, because we don't know if we've correctly specified our model. Sometimes random sampling, that's M2. And then lastly, this one, M5, is almost always violated. But if M1 through M5 hold, which is atypical, but this is like the gold standard, then the OLS estimates are unbiased. Sorry, this should be an M. I don't know why. It's a less than sign. I guess the alligator is eating the 5. I'm not sure why. So this assumption is less likely to be violated in multiple linear regression than simple linear regression because we've taken things out of the error term and put them into our model. But in multiple linear regression, again, M5 is typically violated. So we don't have unbiased estimates, but we're doing the best we can with regression analysis. So if M1 through M5 hold, then the OLS estimates are unbiased. If any one of them fail, then the OLS estimates are biased or on average wrong. And then our last assumption is M6. The error term has constant variance. And so this is what we call homoskedasticity. The variance of our error term, sometimes we do it a conditional on the x's. In this case, I didn't write it like that. But the variance of our error term needs to be constant, which is sigma squared. This is homoskedasticity. If this assumption fails, then we have heteroskedasticity, or the error term has a non-constant variance. So in this case, the variance of our error term equals sigma squared, and then this I means that the error term differs depending on the observation. In the next slide, we can see how to determine whether or not this is violated. We have an entire chapter in the book, chapter 9, that talks about how to test and correct for heteroskedasticity. But in chapter 6, what we would do is we'd create a scatter plot of y against each x and see whether or not the points are scattered in a constant manner around the line. That would be homoskedasticity, or heteroskedasticity, just a non-constant scatter plot. So in this case, homoskedasticity, you can see that all these dots are pretty well uniformly dispersed amongst this line, whereas this is the typical way we think about heteroskedasticity. And then again, we do it for each independent variable. So even if we had homoskedasticity for one of our variables, but or most of our variables, but let's say one is heteroskedastic, our model as a whole is still heteroskedastic. And so in this case, we can see that for low values of x, we have a small variance. For high values of x, we have a large variance. And in this case, if we wanted to use all information, we would weight the observations that are down here. We would give them more weight than ones up here because these offer better information as to where the line is, whereas these offer not as good information as to where the line is. So we'd put more weight on the observations down here, less weight on the observations up here. This is what we'd call weightedly squareds if we knew the exact form of the heteroskedasticity. Again, chapter 9 talks about this. The importance of M1 through M6. If these 6 assumptions happen to hold, then our OLS estimates are not only unbiased, which we need M1 through M5, but they're also blue, which is the best linear unbiased estimator. And best means minimum variance, so that means that you have an unbiased estimator that's linear, then you're not going to find one that's a smaller variance than our OLS estimators. And so this means that among all linear unbiased estimators of the population slope and the population intercept, the OLS estimates have the lowest variance. And in economics, this rarely holds, but yet again, this is our gold standard.